Okay, let's start with basic concepts of functional analysis we have to discuss. First definition, metric space. I choose the black color. Is it a known concept? What we call the metric space?
A linear or a topological space with a function of with a function of two elements that is 0 then and only then both elements are equal, that is greater or equal to 0, that is symmetric, and that satisfies the triangle inequality.
Yes, but the two properties, linear and topological, we can omit now because metric space can be not linear. It is the first. And second, the topology introduced in the metric space after the metric. And we call it the topology of the metric. So yes, you're right. So metric space, it is a pair. X is arbitrary set. And ρ, it is a metric or distance. It is a function on the of pair elements of our set, or it's on a Cartesian product into the non-negative numbers with property. First, for 0 can be only on equal elements. Here I define this non-negative numbers. So it is equal to 0 if and only if x equal to y. Second, it is symmetric function. And third, it is the triangle inequality is valid. So if we take the third point, z, for example, we obtain the following inequality. The basic notion is the complete metric space. Do I need to define the fundamental subsequence or not? Is complete metric space if for any fundamental sequence there exists limit of this sequence, just define it as x, it belongs to the our space. Okay, let's give some examples. For our seminars, we need about 10 or more different examples of metric space. Anybody can?
The usual Euclidean space with the standard square root of sum of squares metric.
Okay. Real space Rn and complex space Cn. Yes. It consists of n-dimensional vectors with real or complex coordinates. Yes. And standard metric Euclidean is square root from sum of squares of the difference of absolute values. Yes? And for the following, when we write some symbols for metric space, this symbol define the set and the metric simultaneously. Yeah? So, but the main topic of the functional analysis that we study is infinite dimensional spaces. So these examples from linear algebra or calculus, but for functional analysis, we must consider the infinite dimensional spaces. So let's follow our list of examples. So if you start from the space of sequences, so I follow by sequences. So second will be from 3 A, B, C examples. C double zero, C zero, and C without any zero, C small. C small with double zero, 1 0, and without any zero. It is infinite sequences. But first space consists from the finite sequences, but this place from which starts the zero coordinates is different for any elements. For the quantities are following. For any x, there exists n, which depends on these sequences x, sequence x, such that for any k greater than this n, xk equals to 0. C with 1, 0, is infinite sequences, but limit equals to 0. And C small without any 0, infinite sequence, such that there exists the limit of this sequence. For example, A, and this A number depends on X. Why we have example in one item? Because it is the metric. The metric in all these spaces I introduce as following. It is supremum of difference of coordinates, absolute values. And it is easy to understand that these spaces are embedding. What you can say about completeness of this space? Let's discuss. The Euclidean space, the finite dimensional spaces are complete, yes? Because all convergence is coordinate convergence. I didn't define the convergence in metric space, but definition is very simple. I remind you, Xn tends to the Xn metric space. If the distance between Xn and X tends to the 0. Yes, it is standard definition. So in the first item, in the first example, all the convergence by metric, it is just the coordinate convergence. What you can say about space C double 0?
I don't think it is complete, because you can imagine a sequence of small elements which gets shifted every.
Okay, let's prove it. So first exercise, C double 0 is not complete. So what is your example?
So imagine a
so-
sequence of n equal small elements of size epsilon,
Well, for example, just more concretic. So when I try to write the sequence in the space of sequences, the number of element of sequence I write up, and coordinate I write down. Okay, indexes. So the second element you can take what? One. One
like yeah, something like that.
So xn looks like, for example,
no, it should
I think it is sufficient. So
okay,
can you show first
yeah,
that
okay.
this sequence is fundamental?
Well, the difference between m for each k, the difference between xk and xk plus m is I think we should make this sequence converge faster, or we won't get.
I think it looks like this: minimum between n and m plus 1. Yes. Is it correct?
I'm not sure.
The
Yeah.
You're right. Just let's see. Xn looks like 1, 1/2, yeah, and etc. 1 over n, 0. Xm, for example, let m greater than n, let, for simplicity. 1, 1/2, 1 over n, n plus 1, 1m, and 0. So this common part will be reduced, yes?
Yes.
And the different stars.
Yes. I'm sorry, I forgot that we work not in L2 but in our
we
metric
work
is
with C0, and in C0, C00, the metric is supremum.
Okay, yes, then it's sufficient, right?
So we see that it is 10 to the 0 as n and m is large, yes?
Yes.
Definition of fundamental sequence.
Yes, but
So
this
but,
limiting sequence it does not belong to our space because
yes,
it has an infinite number of non-zero elements.
From this metric in C00, C0, and C, from the convergence by metric, it following that follows that for any k, the k coordinates converge to the k coordinates. Yes, and we see that by coordinate, this sequence, our example, is not finite. So limit sequence it's a harmonic sequence, yes. 1 over n, 1. So is not fine. So our space is not complete. Okay, let's continue our examples. Third example, yeah. Third example. Again, one-dimensional space, LPN. It is space of the finite vectors, real or complex, with metric equals to one over p, sum from n to n. And what is the diapason for p? What numbers p we can take in this metric? For triangle inequality, we need take p greater than 1. And for this formula, we take it's finite. But if we take the limit of parameter p tends to the infinity, we obtain space L infinity and dimensional, and metric equals to the maximum. And is it evidently that all axioms of metrics are valid for this formula? That is a real metric. Is it clear or not? So it is of course symmetric. It is of course non-negative. 0 we can obtain only on when x equals to y, and of course, and in triangle inequality is just for these spaces is a Minkowski inequality. That's fourth example, LP without any n, so it is fine infinite dimensional spaces with property that corresponding sum is finite. It's for this, and for infinite p, it's supreme. It's bounded sequences. And the
Excuse me.
Yes.
When you write X, E, you mean all the time that they are from real numbers?
No, by in general situation, we consider all spaces to be complex.
Okay.
If we need to consider just the real spaces, we describe this, the element. So the matrix, of course, we can obtain matrix from the formula which describe the elements of space. So for finite, we need to repeat this sum. For finite p, and for infinite, it is just supreme. Yes. So let's start from the examples for functions, the space of functions. Some examples you know from the calculus or from linear algebra, but of course it's from calculus.
Yes, the space C of AB, where AB is a closed interval, and the metric is the maximum of absolute of a value of difference.
So-called Chebyshev or uniform metric, yes? Uniform metric. What you can say about the completeness of these spaces? We don't discuss for item 3, 4. So what we can say about LP finite dimensional, LP infinite dimensional, and for space for continuous functions.
This space is not complete because the limit of a sequence of continuous function needs not to be complete.
The uniform, the uniform limit.
Not the uniform limit needs to be continuous.
We take the uniform metric.
Yes, so then it's complete.
All these spaces are complete. Complete. But for example, I can consider continuous functions with another metric. I define this space in the following. So parameter p shows us that we consider the integral metric. A function are continuous, so we consider the Riemann integral. It is for finite p. But if we take, for example, the limit for the infinity for parameter p, we immediately obtain this. What you can say about the completeness of continuous functions with integral metric?
It's not complete.
Yes. So let's proof exercise 2. For simplicity, C1 non-zero 1 is not complete.
I think you can get a sequence of head-like continuous functions which would converge to an indicator function.
Okay, for you, I write as picture, yeah. I think if we want to can write a formula, but it is sufficient by picture. 1/2, yeah.
Something like just like an interval in the
and n is sufficient. For example, such. Then we take here 1, yes. Here we take the linear part, and then we have 0. Is it clear that in this metric, this sequence is fundamental? Try to write the common formula between function with number n and function with number m. Let's try to. Is it clear that the difference is just the square of this triangle? And the square of this triangle is so here 1. So the height of this triangle is 1. So we have this basis, and by formula 1/2. So it is tends to the 0 as n and m is large, yes. So it is fundamental. But if we want to show that it is not complete, what we must show? Yes, we know that this function tends to the indicator, yes. But what we need to show additional?
The indicator is not continuous function.
Not indicator. You must show that these functions have no continuous limit.
Well, the limit is just a step function, and step function is not complete. Oh, I'm sorry, it's not continuous.
But we can show that it is clear that in metric space we have, if sequence have a limit, then the limit is unique, yes?
But in this metric space, because it's an integral metric, we should kind of identify functions that are equal almost everywhere, but with a continuous case.
Yes.
Two continuous functions equal almost everywhere, they have to be equal everywhere.
Yes. Yes.
So that's why.
So the limit, this unique limit, it not belongs to. Yes, you're right. You just consider the not Riemann integral but Lebesgue integral. Yes, for example, for continuous functions they gives us the same result, but in Lebesgue integrals function the limits are coincide everywhere. Yes, and for continuous function you're right. If two functions coincide everywhere, almost everywhere, they are coincide in any point. Good. Then 7 example I consider n here. So it's index up for these spaces is for the smoothness. So index down is for integral parameter, and index up it is for smoothness. So it is just such functions for that for g equals 0, 1, n, all these derivatives are continuous. What metric we can consider in this space? the two typical metrics, ρ1, ρ2, first, it is idea that to obtain formula which takes all derivatives. So we can take sum with maximum on 0, 1, and then okay. And second type, this take maximum for z at maximum for x. Okay. What is the difference between these two metrics?
Are they going to be equivalent?
Yes, and they are equivalent because we can write this inequality is evident, yes, because ρ1 have all sums. So the maximum element, maximum term belongs to this sum, yes. But we can write another side inequality because we can take maximum, how many? We have n plus 1 terms in our sum, yes. So the convergence to this matrix are the same. We just change some geometry properties of our space, but the convergence from the point of view of analysis, they are not different. Okay, another. So we have omega some universal set. We have M sigma algebra. That we have mu finite or sigma finite measure. And we can describe space LP omega mu. It is measurable functions, yes? Measurable functions. For which such integral is finite. It's for finite P. And for L infinity, how we describe the class of functions?
With finite essential supremum.
Yes, essential supremum. Should I remind what is it or not?
Yes, please.
Okay. Essential supremum is finite. And this is just the function is bounded almost everywhere. So we take supremum not over all set omega, but we can take away some small set A. And what is small of this? All set, which of course measurable and of measure 0, is just essential supremum. And metric in these spaces, for this space we have metric just integral. And for this space we have just essential supremum. So then we consider, I consider only one-dimensional situation for these spaces. So Sobolev space, is it known concept?
If you could please remind it.
I consider only one-dimensional situation, so I write this AB. So n is a smoothness parameter, p is an integral parameter. So it is function absolutely continuous. Oh, sorry, not such. It's such class of functions that for g equals 0, 1, n minus 1, the corresponding derivative is absolutely continuous function, AB. So it is absolutely. And the last derivative is from LP. And for example, for finite P, we can write metric as sum integrals for AB, Lebesgue integral, FG, corresponding derivatives. And on seminars, as examples, we consider n equals to 1 or 2. I think it will be sufficient for us. And it is useful to discuss the Hilbert space with reproducing kernel on these spaces. And for infinity, you must change the integral on essential supremum, yes? Change integral on S sub for P equals infinity. And the last example on today, or not on today's thing, but so called discrete space. What is the discrete matrix space? X is arbitrary set, and metric is very simple. S, which arise a discrete topology. 1 if x not equal to y, and 0 if x equals to y. Is it clear that it is indeed metric? Describe all fundamental sequences.
So all the sequences which have a tail of zeros, or like the tail of the same element.
Why 0? We don't know about
No,
0.
no, I mean like
arbitrary set.
same element in the tail.
Okay, yes, stabilizing.
Yes, stabilizing.
Stabilizing sequences. So x equals x1, x and capital, and they a, and so on. Yes. Can you, so what you can say about the completeness of this space? So let's, I go up, this complete, you must understand. This is complete LP. Sobolev space complete. I take it without proof. And what we can say about discrete matrix space?
So also complete.
Also complete because A, of course, belongs to the X. So from this, we immediately obtain that it is complete. Try to describe all open set and all closed space sets.
Well, it's totally disconnected. So every singleton is an open and closed set.
In fact, every subset of this set is open. Or I'm sorry, of this space is open.
Yes, you are right. Answer all. it's easy to see that one point is open. Yes? But should I remind the definition of open set in the metric space so it is clear? In oral way. Set is open in metric space. Is it with any point consist with some ball? Yes? With silence.
Sorry, I don't understand what is the definition of.
So let's M belongs to X row is open if by definition for any X small from the set M there exists epsilon positive such that open ball with the center X belongs to M. This is notation for all Y from M such the distance of not to M but X by definition is less than epsilon. So what is the question? Somebody have a question for me?
No question. It's just I don't know the definition of. I don't know this definition before. I'm not clear about that.
So from this definition and definition of the discrete metric, it is easy to see that one point is open in X disk. Yes, so it is clear. Because if we take epsilon less than 1, so the distance must be equals to 0. So it is just only point A belongs to this set. So and by the axioms of topology, arbitrary union of open set is open. Yes. The arbitrary union of open sets is open set. So we immediately obtain that in discrete space, all sets are open as arbitrary union. And by definition of the closed space set, if the complement is open. Following definition, the limit point. X0 is limit point for set M from the metric space. What does it mean?
It means every punctured neighborhood of the point contains another point of the set.
Yes. So for any epsilon positive, yes, the ball with center x0 and radius epsilon intersect with set M consist. No, this intersection has many points, yes? And the following definition, just from the limit points, the closure.
I'm sorry, why do we have infinitely many points? Like if we have a discrete, like if we have a finite topology, we can still have limit points, can't we? I mean, like the usual definition is just that every open neighborhood of a point contains other points contain points of the set.
No, it is not a definition of the limit point, you say. It is another notation, it's so-called just the point of touch, I think it's in English. The point of touch, so let's discuss this. X0 is a touch point. You mean this property? Or no? When the intersection with neighborhood is not empty. It's closed notation, but it is another notation, another concept. Because for limit point, we need to have infinitely many points in the intersection. For touch point, it's just not empty. So for touch point, if touch point is not a limit point, it is isolated point, yes? In discrete metric, all sets are contains from the isolated points. So they are not contradiction. Is it clear or not?
Well, the definition on Wikipedia for limit point is like what I said.
We take this definition for limit point, not Wikipedia.
Okay.
Yes? Okay.
I think there is a little difference in Wikipedia. It probably uses punctured neighborhood, so you have to remove X0 from the ball, and then it will be true.
So I don't see the definition from Wikipedia, but I try to guess that you take this. So
should be the case on Wikipedia.
Without X0, yes?
Yes, what I have a problem with is not like the punctured neighborhood, but rather the explicit mention of infinity, because I'm not sure
but you can prove that it is the same. You can prove that these two definitions are the same, the equivalent. Because for any epsilon, and you can take epsilon as a 1 or n, you have a countable set of balls, and the intersection is not empty. You can.
I don't think this holds in arbitrary topology, because we can make
arbitrary topology. It is true. It is don't, but we take metric spaces. We take metric spaces.
Oh, okay.
You can prove that in metric space it will be same. So, and definition which follows from these two concepts is the closure. So what we say about the closure? So we define this as such, and by definition, the closure all limit points. And how we can define the closure with the help of a touch point?
All touch points.
Yes.
We can also say that it's an intersection of all closed sets that contain M.
Yes. But this is more universal. We just can consider for any topological space, but it is not convenient, I think, to intersect all closed space which contains M. Yes. Following definition: set M is dense everywhere. No. This what we can omit. What does it mean? The set is dense on X.
Closure of M is X.
The closure of M is just X. And very important definition: separable space. X is a separable metric space.
Well, if it has a countable dense subset.
What you can say about discrete metric?
For every point,
For discrete metric, we need for countable additionally consider finite or countable. So exist X0 and X countable.
Is it me or did the sound just bug out?
What?
Was it me or has the sound just bugged out?
I think it was okay.
So you don't hear me or what?
I didn't hear you for a second.
Just now?
Now I hear you fine, thank you.
Okay. So exists a subset X0 countable or finite. And I think this part just for discrete metric. Such that X0 closure gives us X. So let's briefly consider our list of example of space and try to answer what we can say, and try to say something of separability of these spaces. What spaces are separable or what not separable? For example, X discrete, when is separable?
When it's at most countable.
Is separable if X is finite or countable. Second example, what you can say about space of continuous functions? For simplicity, the real valued functions.
I think it's separable.
It's separable. Why?
You can take polynomials as an approximating
By
set.
Weierstrass
rational.
There exists polynomial, yes?
With rational coefficients.
Such that the norm for any f, there exists polynomial such that this just less than epsilon, yes? And second step, we can consider, for example, the of degree n, and we take ci from rational numbers, yes? And the set of such polynomials is countable. Can you give me example of not separable space, not discrete, which is not countable from our list? Can you find?
I think LP spaces are not separable.
LP small or LP large?
LP large.
If metric, if measure is finite dimensional, is sigma additive. If measure sigma additive, what I write for LP? Maybe I write something strange. No, sigma finite. Yes, if measure mu is sigma finite, then for finite p, the spaces are separable. But by definition of measurable functions, it is a limit of simple functions, which is a linear combinations of indicators. And then you can just consider the set of such indicators by definition of sigma algebra that you can construct the countable dense set for finite p. Okay, but infinite. So let's exercise what number of the exercise? 3, yes? It seems to me by 3. Let's show that L infinite is not separable. To show it, let's I prove short lemma. I should prove I prove simple lemma. Let X through metric space and then exist M and X not countable such there exist positive number D that for any X, Y from M, the distance between these elements not less than D. Then I claim that space X is not separable. By contradiction. Let X is separable. Then exist X0 and X finite or countable such that the closure of X0 gives us X. But I claim that this is equivalent to the such property. For any positive epsilon, let's consider balls with center and X, where X belongs to X capital 0 and radius epsilon. What we can say about the union of these balls, of all these balls for any epsilon?
It's X because
by definition of limit points,
yeah.
All these balls contains all limit points, yes. And we as center we have just the set X0. So we have set X0 and we have all limit points. So it just X by this. This is the closure. So what we can say about the number of these balls?
It's not countable.
Why?
Oh, I'm sorry.
We take by centers
on the contrary, it's countable. I'm sorry.
number of balls, just the same as the x0. Yes. Finite or countable. But then we have set M, yes, in lemma, which is not countable. So what we can say? M is large set.
There exists such 2 points in M that at least
but I
at least one.
Let's start
that at
from
least
the
one.
from the ball. I planned it. Yes, you're right, but I start with the ball. Exists ball. Yes.
Yes, such that 2 points from
consists 2 points x, y from M. Let's take it epsilon. Let's take d over 3. Yes. Then we have d by property of set M. We have this inequality, and by triangle inequality we have contradiction because it equals 2d over 3. It is not valid. Yes, contradiction. So it is finish of our proof. Yes, is it clear?
Oh,
this was the basic idea.
So
Yes.
the short statement of the lemma is that if there exists a lower if the distance between points in an uncountable metric space is limited from below,
yes,
then this space is not separable.
Yes. Yes. And just come back to our space L infinity. So by lemma, it is sufficient to introduce a set M which is not countable with this property. With inequality from below. Why I prove lemma? In order for more simplest way to prove that L infinity is not separable. Let's consider sequences from 0 and 1. What you can say about the power of this set?
It's uncountable.
It's uncountable by counter diagonal methods. Is it clear for anybody?
It's uncountable because we can a subset of this set encodes numbers like binary binary representation of a unit.
For example, or you can consider the so-called counter diagonal method. Anybody know a counter diagonal method?
Yes.
If you suppose that it is countable, you can count all elements, yes, but so you can write it in the table. Then you write the diagonal in this table and change any symbol to the opposite symbol. 0 you change on the 1 and one you change on the 0, and you introduce a new sequence which is not in table. So we don't count any elements. So it is uncountable, and the distance between two elements is 1 as x not equal to y. Yes. So we just have a situation of lemma. Is it clear or not? Oh, silence. So
yes, it's clear.
Let's move further. The maps on transforms of functions so we have two metric spaces, X with metric rule, and immediately suddenly Y with metric D, not Greek letter, and we have a map F. So what type of maps we will consider? F continues in point x0. Need I to give a full definition, or it is clear concept? Is, yes, is uniformly continuous. I suppose I correctly write it. What Lipschitz map?
Yeah, could you please remind this concept?
Lipschitz or all previous?
Lipschitz.
Lipschitz, okay. There exists number R non-negative, such for any such that supremum all x and xy from x d f x f y here and this is constant of Lipschitz constant. And Lipschitz maps are very important, for example, in many cases and many districts. It is modern thinking in machine learning, for example. And you know that, for example, for differential equations, there is the theorem of existence and uniqueness of the solution. We consider the Lipschitz right side of the equation. So we would consider for differential equations the Cauchy problem, function g of x, independent variable, and function y, function and starting value. Then we need the property of function g capital must be Lipschitz on variable y. So then you can prove the theorem of existence and uniqueness of the solution. Is it clear that the Lipschitz is uniformly continuous?
Yes.
Okay. Contraction. Is a contraction map. If R in 4 is less than 1. Does this R, this value R in point in item 4 is less than 1, then it is contraction. And sixth definition, sixth property is isometry. We can distinguish full situation or partial. So a full F is the action from X to Y and partially isometry F is not the action. But of course, if we have, we have that it preserves distances. Of course, with this property, any map is injection, of course, yes? But the range of F is not, or image of F is not all Y. So in this situation, we can name it is a partialism. So it is the more important properties of maps which we continue consider, and then some words about properties of complete metric space. The simple property that in complete metric space we can take a limit and guarantee that the limit element has the same properties as pre-limit elements, yes? As elements which converge to the limit. For example, if we can consider the space of differential, for example, functions, and if we know that it is complete, then the limit function will be differentiable, yes? It is very useful property just from the definition of completeness. But another, I remind you 3 theorem, and we discussed which what of these theorems we need to prove, or it is known facts for you. First theorem is the theorem on a fixed point. Let is complete metric space and F is a contraction map. Then there exists unique point X star from X such that Fx star equals to X star. So called the fixed point theorem. Is it known fact or we need to prove it? Simon. Is it a known fact or not?
Yes, it is.
Okay. So give me an example of not complete space for which it is not valid. Who can?
Well, consider the rational numbers, and rational numbers are a metric space which is not complete, and any contraction on rational numbers that in real numbers has an irrational limit, this contraction would be like for this.
Try to.
For instance, take pi, like image of x is pi plus x minus pi divided by 2.
X plus
f at x, no, it's pi plus x minus pi divided by 2.
Pi?
Yes.
Plus
x minus pi divided by 2. This whole the whole thing is divided by like x minus pi in the numerator, and in the denominator 2. No. Pi is outside of outside of numerator. The other pi, the left pi.
X
like
this, then it is the denominator, yes?
No, we have separately pi,
okay.
And separately x minus pi divided by 2.
Pi plus
yes.
Such?
Yeah, you can simplify this, but I think in this forum it's like more clear
But
why.
I'm afraid that it is not from x to x. For rational number, you can obtain not rational number because you have pi.
When you have you consider the root of
I understand what you want to obtain, but
okay, consider the root
we
of
have this property, yes, this. But for this, maybe more simple.
okay,
Let's consider more simple examples. For example, not rational, but real without zero.
Okay, yes, then you just can divide by a certain number and it will be a contraction, but with no limit point.
For example, yes, with standard metric. For example, this contraction is, of course, has a fixed point in real axis, and x star just equals to 0, but we take 0 out from the space, yes? Okay, I give idea of the proofs, only idea. Because for some tasks, it will be convenient. Let's x0 arbitrary starting point. Start point. Then you take x1 equal to f at x0 and etc. By this rule, you obtain some sequence, yes? Then so-called orbit of the point of the starting point x0. So we obtain sequence xn. Then you prove, we can prove that this sequence is fundamental. So as our space is complete, then exists limit. Let's name this limit x star. Then we can prove that f x star equals x star. First step, second step, and last step, we can prove that for any another point y star with property f y star equals y star, it follows that these points are the same. This is idea of proof of this. So if you know this fact, then we not discuss it in details. Second theorem. Let's define the system of, I don't know, nested maybe. Yes, no, who knows? Nested balls. Of nested closed ball. We have Bn just B, Xn, Rn closed balls. Some remark on notations. I repeat the definitions. It's from X, such that it is open ball, and with the square brackets as open interval as and closed interval. Closed ball. Okay. It is easy to check that open ball is really open set and closed ball is a closed set. And the system of nested closed balls means that B1 contains B2, contains B3, may be equal, Bn contains Bn plus 1. And theorem 2, let we have some metric space. Some metric space. It is complete. It is complete. if and only if for any system of nested closed balls with property radius tends to 0 exists unique point in intersection of these balls. Is it known fact or not known fact? The theorem of the system of nested closed balls. Okay, let's prove it then. First, it will be first, I prove this direction. So we have complete metric space. And let Bn our system. Yes. With a radius tends to the 0. Consider the sequence of centers. What we can say about limit of these centers? Fundamentality. Let for simplicity n greater than m. What you can say? Then ball with center xn, rn lies in ball with the smaller number, with the ball with number m. Then what we can say about this distance? It is the center of radius. Yes. In general situation, we can take the maximum between two. Yes. And of course, it is tends to the 0 by our property s rm as m tends to the infinity. So the sequence of center is fundamental. So it, by completeness of space, there exists limit, which I denote as x star. And what we can say, as it is a limit of xn, so the intersection of all balls is closed. And x star is a limit point. Because it is a limit. So we immediately obtain that x star belongs to intersection of all balls. Yes. And if we have another point, if exists a star another point, then which is belongs to intersection. Yes. then we immediately obtain that the distance between x star y star less than by triangle inequality. This sum take the center of nth ball, and we obtain that it is less than 2rn, and it is tends to the 0 as n tends to the infinity. So we immediately obtain that x stars coincide with y star. So the first step of our proof is finished. So another implication, let we have the property that all nested system of closed balls is not empty. Moreover, it consists unique point. We need to prove that our space is complete. So let's take the arbitrary fundamental sequence. What we can say? By definition of fundamentality, I said there exists such number n1, natural, for any n which is greater or equal n1, the distance between xn xn1 less than 1/2. And first ball I take as ball with the center, oh, this, not x1, xn1. First ball I take xn1, and radius I take u1, 2 times larger than this. Then by induction, exist n2 larger than n1, such that for any n which is greater or equal to n2, the distance between xn xn2 less than 1/4. And the second ball, I take the ball with the center xn2 and radius 1/2. It is easy to check that it is nested. Why? Let y belong to B2, and then calculate the distance between x and 1 and y. It is less than x and 2y plus x and 2 x and 1. This term y belongs to second ball, radius equals 1/2, so it is less or equal 1/2. And here n2 greater than 1 n1, and look at here, it is less than 1/2, so sum less than 1. So we obtain that y belongs to B1. And by induction, if we construct B1 nested B2 nested Bn, when Bk equals sum x and k, and radius we have 1/2 power k minus 1, the second 1/2, first unity radius. So we say that there exists here m and here m. Exist n m plus 1 greater than nm, then for any n distance between x and m plus 1 and x and m we have, it is at the center of the last ball, less than 1 over 2 powered m, and then we take next ball m plus 1, which is with center this number and radius 2 times larger. And we can show analogous this property. It is the same as we show here. Then we construct the sequence of centers. It is fundamental by first step. And we know that, but not xm, but x n sub m. And we know that exists limit it x star. We don't know. But what we show, it is only subsequence. This is only subsequence of our fundamental sequence. But easy to check that all sequence tends to x star y, because by triangle inequality we have such formula. This is go to 0 as m tends to the infinity, and this goes to 0 as m n tends to infinity by fundamentality. So we show that whole sequence tends to the same element.